Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at our malloc function that allows for us to allocate memory dynamically in our C program. This video is part of a larger series of videos focusing on the use of pointers in the C programming language, and it also assumes that you've watched the earlier video, malloc_01. So the first thing we want to do is we want to obtain a copy of our malloc_02.c snips file, and you'll notice that I provided you a background link at the top of the snips file. That is for the Wikibooks page focusing on the malloc function. You'll also see a couple of function prototypes. We're only interested in this malloc_02 because we've already handled the display int array in the earlier video. The display int array simply displays the resulting integer array as we populate it. So to begin with, what you want to do is you want to go ahead and copy your function signature, your prototype, over to our list of prototypes in our pointers driver.c, as well as go ahead and copy over the start of our function implementation. Last thing that we want to do is we want to go ahead and update our main to be able to handle the appropriate switches. In this case, I'm just going to go ahead and borrow the code from the malloc_01 and change where needed. And I'm also going to go ahead and update the help. So in this case, just make a copy of our malloc_01 switch help. And once again, I encourage you to update this when you have time. At this point, we can go ahead and close out our snips file and we can get started on understanding what this particular example is all about. So in this case, I'm just going to go ahead and right click, go to the declaration definition. Specifically, I'm going to right click on where I've called my malloc_02, and it will take me down to the implementation of our malloc_02. So what's different in this particular example, or what's the point of this example rather? Our goal with this example is to understand sort of some of the limitations of our malloc function. If you recall from an earlier video, it allows for us to allocate the memory associated with an array, or for that matter, other data types such as structures, or rather not data types, but data for other data structures. It allows for us to allocate that memory at runtime. So in other words, instead of hard coding in a specific value for the size of an array, we can allow, for instance, for the user to select that at runtime. Also, this allocates the memory on the heap, not on the stack. And so would encourage you to go back and also take a look at our stack versus heap video to understand a little bit about the different types of memory. So how are we going to demonstrate this? Well, the idea here is I want to provide the user an opportunity to dictate the size of the array and then populate it by asking them some questions. In other words, asking them to enter in a value. Once our array has reached the size that they have initially allocated, we want to automatically create a larger array. In other words, we want to extend that array. But the problem with it is that malloc simply allocates a block of memory. It's then up to you to fill it. So if we've exceeded the initial allocation, essentially, we have to create or allocate another block of memory and then update that new block of memory with the existing information. And what you'll see here in this demonstration is that there's a couple of steps involved, and it's perhaps a little bit unwieldy, but it's important for us to understand the limitations of malloc so we can see what other functions are at our disposal. So to begin with, much like in the earlier video, what I want to do is I want to set up some variables to be used for management, in this case, one of which is going to be our results variable. And that's just simply going to dictate then our return value. And we'll go ahead and start off by initializing this to exit success because we're going to be optimistic here. And then we're only going to flip it over to failure if there is in fact a problem. So in this case, I want to go ahead and return my results. We also want to create two pointers to an integer array. As I mentioned earlier, we're essentially going to have to copy over the values once we've enlarged our array. And to accomplish this, we're going to actually need two arrays and therefore two pointers to integer arrays. And I'm going to call this first one my current, essentially my current array. And then I'm going to have another one that I'm going to call my new array. And so the idea is that once the user has exceeded the initial limits that they prescribed, that we're going to create a new array that is one larger than the current one. We're going to simply move all of the values over to the new one. We're then going to extend the size of the current one, and we're simply going to copy them all back. To be able to do that, we also need to be able to store then the total number of elements in the array, or how many elements have been allocated currently, as well as keep track of how many of the elements have actually been filled in the array, because remember that an array can essentially have uninitialized values. So for instance, you can have 10 elements in the array, but you're only actively using 5 of them, so we want to be able to keep track of that. And in addition to this index filled variable, we will find ourselves also wanting to simply have an index variable, as well as a way of temporarily storing values that may be retrieved from the user. And then lastly, we're going to need a flag variable called done that will allow for the user to tell us when to stop. The reason we need this, and we didn't need it in the earlier example, was in the earlier example, we didn't allow the user to ultimately continue adding elements to their array. So in this case, we need to come up with a graceful way in which to exit our application. And so if you think about it, if the user adds the total number of elements, or excuse me, adds elements that fill up the array to the n max, or essentially fills up the existing array, and we continue to extend the array, we need to have a graceful way to stop this process. And we'll see how to go about doing that. So at this point, what we want to do is we want to initialize some of our variables here. We'll start off by initializing our n max, even though we're going to capture it from the user, but you'll see why in just a second. We're going to go ahead and initialize our index as well as our index filled, because in this case, the index filled, we want to assume that we start loading or updating the values in our array from the 0th index. We also want to go ahead and initialize our value. And then we want to set our done flag equal to false. And at this point, the last step that we want to go ahead and do, we haven't seen yet before, we only talked briefly about it in the malloc_01 follow-up video, is we want to initialize these two array pointers to a null value. And essentially what that means is that they are pointing to a null value. And so in this case, we want to do it with both our current and our new. Why do we need to do this? Well, because if you recall, when we declare a variable, we can't guarantee what its initial value is. So just as a gentle reminder here, we are declaring the variables here. And the values are essentially garbage. And we understand a little bit about what that means when it comes to an integer, for instance. But what does that mean when it comes to a pointer? Well, that simply means that we have no idea where current points to. Neither do we have any idea where new points to. And what we want to do is, in the beginning, is we want to go ahead and say that they essentially point to null. And rather what we're doing here is we are setting those values equal to a integer pointer value of null. Now, how are we going to go about initializing our first array? Well, we said that we want to ask the user how many elements they would like in the array. Well, that's why we wanted to go ahead and initialize our n max equal to 0, because this allows for us to have a nice little while loop that while n max is less than or equal to 0, we simply prompt the user. So with a nice printf here, we say, please enter a positive integer for the initial size of the array. And we'll follow this up with a new line and a scanf where we simply capture our %d and we store it in the address of our n max. Now, if you think about it, this while loop will work perfectly if in the case that the user is not paying attention and enters in 0 or a negative number, it will simply just reprompt the user. The only way that the user can get past this while loop is by entering a positive integer value. At this point, what we can do is we can allocate the initial array. And to do so, we'll do something similar to what we did in our earlier video, in that we will assign to the current variable the return value from malloc. Specifically, we're going to cast the return pointer from malloc into an integer pointer. And remember that malloc is going to return the address to a location in memory that has been allocated based on the size of the data type and the number of instances of the data type we want. So in this case, what we want to do is provide to malloc the nmax times the size of, and in this case, we're going to use the size of an integer. So whatever the size of the integer is multiplied by the number of elements will be the total amount of memory returned by malloc, allocated by malloc. The address of that memory then will be cast to an integer pointer and assigned to the current variable. So we're going to make a quick note here, is that this is the address of a block of memory. Now, as always with our malloc, we want to be a little bit pessimistic in that we want to assume that it is possible that malloc failed. And if that's the case, then it is going to return null. That simply means that it could not, in fact, allocate the memory, in which case what we want to do is we want to provide a printf and an error that simply says failed to allocate enough memory. And at this point, then we simply want to assign the value of exit failure to our results variable. And then under the else branch of our if else, we want to do something. And what does that something look like? Well, that something looks like merely now populating the array. And so the idea here is we want to ask the user what values they intend to store in the array. Now, we could have done this any number of ways. We could have captured it from the command line. We could have also captured this from a file. But for this particular example, we'd once again like for this to be interactive. And to accomplish that, we are now going to leverage our done variable. And our done variable, our done flag, will simply be used inside the while loop, so that while done is essentially equal to false, we want to collect info from the user. And the info that we wish to collect is simply a positive integer that we can then place in the array. Now, there is no reason necessarily that it couldn't be a negative integer for the purposes of this demo, but what I'd like to do is I'd like to mix in a little bit of validation into our function here, or into our while loop. And so the first thing we want to do is provide a prompt to the user that says, please enter a positive integer. And specifically what we want to do is we want to communicate to the user where that positive integer is going to go. And in this case, we're going to place it in the array at a given index, but we also want to allow for them a way to get out of this while loop, because if you recall, the whole goal is that we initialize our array to a certain size and then continue to allow it to grow if the user has more data. So we have to provide them with a way to get out of the while loop. And in this case, if they simply enter in -1, we're going to allow them to exit. And we simply then want to provide in that placeholder the value of the index filled array, the index filled integer. Remember that the whole goal here is that the index filled keeps track of how many values were actively updated in the array, and that may be a smaller number, at least initially, than our n max. At this point, then, what we can do is we can once again use a scanf with a %d, and this time what we're going to do is we're going to update or populate the value of the value variable. And the benefit here with this temporary variable is that now we can do some basic validation. And so in this case, the first thing that we want to check is if the user did in fact want to exit our executable. In other words, they had enough, they didn't have any more data to enter in, at which point then we simply go ahead and set our done equal to 1, which effectively corresponds to true. And we want to print out a nice message to the user that says, thank you for using our malloc demo. Now, if the value was in fact not equal to -1, but we still wanted to have a positive integer, we would want to follow this up with an else if, and an else if specifically that would check to see if the value was less than -1, or, since we're being rather specific here, value equal to 0. And so hopefully you can see here that we've snuck in a little more validation, a little more logic into our application here. And essentially then what should happen if they enter in a value that's less than -1 or equal to 0, specifically less than -1 or equal to 0, what should happen? Well, you'll see in just a second, we actually don't have to write any code here. We just simply have to trap that condition, and you'll see why in just a second. Under the else branch, then we assume that we have gotten valid value. In other words, they've entered in a positive integer, at which point then essentially what this does is this says that our value is in fact greater than 0, and now we can work to assign that value to a specific location in the array. However, it's not quite that simple. What do we do if the array is completely filled? In other words, in the beginning, it's no problem. We simply put it in the 0th location, and we then reprompt the user for the next value. But at some point, we're going to fill up that initial validation, that initial allocation. And in this case, then we want to have a little bit of logic to decide how are we going to populate that array when we don't have any additional room. And to handle this, what we're going to do now is we're going to leverage that index filled variable. So if our index filled is less than our n max, we don't have a problem. We still have enough room. And at this point then, all we do is simply assign the value at our index filled, or we assign the value to the location in our current array at the location index field. So in this case, current square brackets index field is equal to value. And at this point, then we simply increment then our index field to indicate that we've added a new value to the array. However, under the else, then that means that we do not have enough room. And so our first step then is going to be to leverage our new integer array pointer. In other words, our new variable. And the first thing that we want to do is we want to allocate it now to the same size as the existing array. So in this case, then, we'll simply say new is equal to, and remember that the malloc function will return an address to a block of memory that we then need to cast to an integer pointer. So in this case, what we're going to do is we're going to call malloc. We are once again going to use our nmax times the size of the int. So in other words, what we're doing here is we are creating a second array of equal size. And at this point, then what we're going to do is we're simply going to copy all of the existing values over. And to do that, we're simply going to have a for loop. And our for loop then is going to loop through each of the values in our current array and simply make a copy over to the new array. However, before we do that, we always want to check that the malloc function did in fact return a valid block of memory. So in this case, we once again want to simply check to see if our new is equal to null. And if it's equal to null, we can just go ahead and borrow the code from earlier. Basically, what we want to do here is we want to print a message to the user that we failed to allocate enough memory. And we want to change our results from exit success to exit failure. But more importantly, there is an additional step in this case that we want to do, because whether we like it or not, our application has essentially failed. And at this point, we are now done. So what we want to do is we want to set done equal to 1, such that now when it comes back around to the while loop, it doesn't attempt to collect another piece of information from the user. Now, under the else block of our if else, we want to do something. And that do something is in fact copy all of the existing values over. And what that means is we'll simply use a for loop starting at index equal to 0, continuing while our index is less than our nmax, and we simply increment now our index. And copying it over to the new array is simply as straightforward as it sounds. In this case, we're simply going to do new index is equal to current index. And so essentially what we're doing is copying it over location by location. So copy location by location. Now, how do we actually successfully add the new value? Because so far all we've done is we've created a duplicate copy of our array. Well, to do that, what we want to do is we want to go ahead and first destroy the old array. So we'll start off, because once we've safely copied all the values over, we can use the free function to return that block of memory to the computer or to the system. So what this does is this frees up our old or current memory. Now that does not mean that it changes the value in our current current integer array pointer. What it does mean is that that current integer array pointer can't guarantee that something else won't change the values at that memory location. In other words, there may be another call somewhere in your code using malloc that might then use the same memory location. Well, once we've done this, then what we can do is we can now utilize that current integer array pointer one more time. And once again, we'll make a call to malloc, casting it to an int pointer. At this point, though, what we're going to do is we're going to leverage our nmax plus 1, because we want to grow it by 1 element times our size of int. Once again, we want to check to make sure that we have successfully allocated the memory, and if we have not, then we want to gracefully exit our while loop, and that's essentially going to be the same process that we did earlier with checking our new array pointer. And at this point then, under the else, we simply copy the values back from new to current. And to do that, we once again have a for loop starting at index equal to 0, index less than nmax, index plus plus, and this time it's just the reverse. We say current square brackets index is equal to new square brackets index. So hopefully you can see that essentially it's the reverse of what we did up here in the earlier for loop. We are once again copying location by location. And at this point then, what we want to do is we want to store that additional value. In other words, so far we've completely ignored that value. Okay? In other words, we've collected it from the user, we've validated it, but we haven't actually put it anywhere yet. And so to do this, we simply say current square brackets index filled is equal to our value. We increment then our index filled, much like we did earlier when we had enough room in our array. And we also go ahead and increment our nmax, because if you recall now, we've grown the size of the array by 1 integer. At this point, the only thing that we have left to do is we need to do a little bit of cleanup, in that we want to free the memory associated with our copy. And so this frees the memory associated with the backup copy. Once again, we're not going to actually change the value stored in our new integer array pointer, but rather at this point, after calling the free function, you have no guarantee that that memory will in fact not be used somewhere else. Now, at this point, let's go ahead and build it, just to verify that we don't have any mistakes in our code. That looks promising. And what we'd like to do is we'd like to introduce a little bit of noise into our function, because right now, aside from the prompts to the user, we won't really see much happening. And to accomplish this, we're going to leverage our display function that we wrote earlier. And so if you see here, the point of the display function is to simply print out all of the elements in the array up to a certain length, except under the situation in which the user has provided a negative value for the array or a 0 value for the length of the array. And additionally, it also checks to see if the array pointer points to null. So at this point, what we want to do is we want to go ahead and make a couple of calls to our display function. And what we're going to do here is we are going to simply display the array current, and we don't have a value associated with it right now, or a length associated with it right now. So at this point, then what we're going to do is we can either put in the value of 0, or what we can do is make this call right after we have collected the n max. Now, please note here, we haven't actually allocated any memory at this point because we've not made a call to our malloc function. So if anything, this call will simply test to make sure that the logic in our display function is working correctly. We also want to go ahead and make a call to the display int array utilizing our new array. Once again, remember that both of these at this point should have values of null, so they shouldn't result in anything being printed other than a warning. And then what we'll do here is we'll add one more printf here just so that we have a little more information. And how about if we just indicate which array we are trying to print. Now notice here, I don't have a new line. That's intentional. And I'm also going to go ahead and be very careful about the number of spaces I have here because I want us to be able to see this in a nice tabular form again. And then while we're at it, why don't we go ahead and make a quick comment about what we've done here. And so this is where the array pointers or the integer pointers are equal to null. So this is after initializing them to null. And we can once again make this look a little nicer here with a printf and maybe a nice border. As well as a printf and a new line at the end. Now, some of this is going to be a little extra here, but the idea is that we'd like to sort of understand the process of how this works. So after we have used malloc, in other words, after we have successfully allocated enough memory, I would like to make the call once again. And so in this case, this is after allocating our current array. And if you'll notice here, we aren't really going to change much about the array sizes. We're simply going to insert the values. So every time we insert a value, I want to see the resulting array. I want to see if there's any changes with respect to memory, any changes with respect to size, any changes with respect to the values inside of them. So what I'd like to do is inside of my while loop, except at the end of the while loop. So I've got to find, there we go. What I'd like to do is I'd like to simply then print out, once again, the values associated with both our current and our new arrays. So in this case here, what we're going to do is print out the values and the addresses after each iteration. Now, remember I said that this new variable was essentially a disposable or a backup copy. What we want to do is we want to see what happens when the free function is called. In other words, are there going to be any changes? So what I'm going to do here is I'm going to make another call here to our printf, and I'm going to put in after freeing the new memory, and all I want to do here is once again put a nice little border here, and then simply print out the array and see if there's any changes to that array. And really, to highlight this, how about if we make a copy of this and place it before our call to free? And you're going to see this is going to end up being quite noisy here. What we want to do here is we want to focus on the behavior of the free function as it relates to our new. Now we can do the same thing with our current, but we don't want to make this too noisy. Let's see how this looks here. So I'm going to go ahead and build this. I'm going to go ahead and change directories over to our pointers demo. And at this point, I want to verify that our pointers demo, the help works. At this point, I've got a slight problem here. I apparently have eliminated the logic that associates it with calling help if their user did not provide any switch at all, in which case we can update that quickly. All right, and so at this point then what we want to do is we want to make a call to our malloc underscore 02. And what I'm going to do is, once again, I'm going to try to split my screen. So that we can see both the console and our code. And so you can see here, please enter a positive integer for the initial size of the array. We're going to keep this small enough so that we can work through this in our video, but I encourage you to make it a little larger. You'll see that we got a nice little table that says after initializing them to null, you'll see that we're getting an error that says no elements in the array. That's great. That means that we're actually doing something here. You'll also see here that I get something other than that when I make a call to it after allocating our current array. I'll tell you what, let's stretch this out real quick so we can see here that length is 3. We have garbage values, but we also have memory locations in parentheses, and you'll see that those are sequential memory locations, but our new array still says no elements in the array, and essentially it's because it is being passed as null. We'll put in a value of 123 for our first element in our array. So you'll see that we're successfully populating the first element in the current array, but no changes to new because we haven't exceeded our capacity yet. We'll put in a second value here. So this is going to be the one at index equal to 1, so 234. You'll see that I've now updated the second location in memory, and still no changes to the new array. And our third value, or index equal to 2, put in 345. We've now filled our current allotment, but we're being prompted now for another element or another value. So we're going to put in 456, and you'll see now that the length of the new array and its values are going to be 1, 2, 3, and there is a fourth value here that is going to be associated with our n max, but this is going to be because our new array is utilizing our call to the, to the display function with our new array is utilizing our n max. We have not allocated that much memory to our new array. So what we want to do here is we want to come down here into our logic here, into our if statement. You'll notice here that before we free the new memory here, we have our n max. This needs to actually be n max minus 1, or what we can do is we can shift this n max down to the bottom. This is just accidentally copied and pasted this into the wrong portion here. So there we go. And then always remember that our new array is going to be one element smaller than our current array. All right, so one more time, let's go ahead and build it. We'll go ahead and clear our screen. We'll rerun our demo one more time. We have 3 elements in our array. For the first value, I'm going to put in 123. It updates the first value with no changes to the second array. The second value is 234. Still no changes to that second array. 345. We've now updated that third element in the first array. No changes to that second array. It's not until I try to put in a fourth value that my new array pointer, my new integer array pointer, gets initialized to something other than null. And it's still set at 3 because remember that it's always going to be one smaller than the current one. And you can see here then that where I'm storing those values. But notice here, even after I make a call to free, I have not, in fact, changed anything about what the new value points to, the new variable points to. It just means that we can't guarantee that these values here won't be overwritten. Notice here that the 2 locations are still the same. And you'll also notice here that my new array is, or excuse me, my current array is now 1 element larger than my new array. And more importantly, you'll see there's my 456 that is now stored at the 4th location. Also take a second to notice here that my addresses, particularly for the current array, so we'll see here is B0 once it's grown to 4 elements, B4, B8, and BC. But if you take a look up here, it was B0, B4, B8. And so essentially here, what I'm doing here is I am allocating now a new space of memory. And in this case, take a close look, you'll see that it is 0 CB0 for my current array when there are 4 elements. And if you notice earlier, it is 0 CB0 for my 3 element array. This is not guaranteed, okay? So it is quite possible that you will not, in fact, get the same initial memory location, especially when your array starts getting larger and larger. So it is no guarantee here. In this particular case, it just so happens that we ended up with the same location. So our 80 or 0 CB0 and our 0 CB0. Part of the reason why this happened was because I made sure to free up my current array, or freed up the memory associated with the current array prior to initializing it again, or in other words, allocating more memory. And we can continue with this here. We can add some more values here, and you'll see that I'm going to continue to grow the array dynamically. As a matter of fact, you can see exactly what I was pointing out here, that after one more iteration, I went from 0CB0 as my initial element address to 0CE0. So there's no guarantee where malloc will allocate your new block of memory. So hopefully you found this video useful. And more importantly, hopefully you understand some of the limitations of malloc, in that when we have to control our own memory management, in other words, we have to grow our arrays using malloc, then we have to figure out a place to temporarily store those values. And in a future video, you'll see that there is an alternative to this. Once again, if you've got any questions or comments, don't hesitate to email me, and thank you for watching.